Hello and welcome to the Daily Space. I am your host, Dr. Pamela Gay,
And I am your host, Beth Johnson.
and we are here to put science in your brain.
After running through stories that came out during our hiatus, we'll be joined by Dr. Julie Rathbun, a senior scientist at the Planetary Science Institute, whose research focuses on one of my favorite topics, icy moons, as well as my very favorite moon, Io. But first, let's get to all that news.
We're going to ease you into the science today with a pretty picture. This image, which you can see on dailyspace.org in its full resolution glory, this image highlights the supernova G344.7-01. Light from this exploded star first reached Earth 3 to 6 million years ago. Located 19,000 light years away, this still hot nebula allows researchers to study the middle stages in a supernova's slow expansion towards invisibility. This particular nova is the result of a white dwarf star becoming unstable after cannibalizing another star's mass. Stars like ours will eventually puff off their outer atmosphere as planetary nebulae, and the remaining hot white dwarf is nothing more than the core of the original Sun-like star. White dwarfs are supported by the pressure of all the electrons in the star. Electrons naturally repel one another, and due to the Pauli exclusion principle, electrons can only have certain energies and states. If a white dwarf gets too much matter added to it, the electrons can no longer support the star, and the system collapses and undergoes wild nuclear reactions. Researchers combined images from the Chandra X-ray Observatory, the now retired Spitzer Infrared Telescope, and radio data from the Very Large Array and the Australian Telescope Compact Array to create this image. The Chandra data in blue showcases the sphere of expanding nebula in an amazing false color rendition. And like a bubble in modern art, this bubble is painted with cooler infrared in a false color, green. This light shows where the shock appears to be interacting with surrounding materials. False colored red radio emission further highlights the structure of this expanding nebula. The Chandra images in this composite were acquired to allow researchers led by Katori Fukumoto to study the distribution of heavy elements in the nebula. Per their paper in the Astrophysical Journal, they found a clear stratification of heavy elements with a centrally peaked distribution of the iron ejecta surrounded by intermediate mass elements like silicon, sulfur, argon, and calcium.
You know, there is no reason not to just keep going with the pretty science. This is a space show after all, and space is filled with all kinds of shiny, pretty stuff. In our next stop through the universe, we bring you the merging galaxy pair ARP 91. This system consists of two large spiral galaxies that are gravitational pulling one another together. It is still early days in this particular merger, and these galaxies don't yet show very much distortion. When galaxies merge together, it isn't a single collision. Rather, the systems come together and pass through one another before being drawn back together again over and over. These passages can trigger star formation, as is seen in a new image from Hubble Space Telescope. It can also use or knock out the galaxies a lot of the remaining material that doesn't form stars. In the end, where we see two dusty star forming galaxies today, there will be one large red elliptical galaxy that is no longer forming stars.
As the story goes, galaxies in the early universe could form in all sizes through the collapse of massive clouds of gas. Over time, smaller galaxies would continue to form through the collapse of gas into stars, but new, larger galaxies would only be formed through the merger of smaller systems. It's a good story. But the question becomes, at what point does this break down? Just how small of a system can form through mergers? To find out, researchers examined the stellar population of the nearby Large Magellanic Cloud. This southern hemisphere sky object looks like a cloud reflecting back light, but is actually a dwarf irregular galaxy. Using the Very Large Telescope and the Magellan telescopes in Chile, researchers led by Alessio Marisorelli studied the compositions of stars in this galaxy's various globular clusters. When a galaxy merges with a galaxy, the resulting system contains the globular clusters from both systems. And these cluster stars reflect the chemistry of where they formed. And one of the observed globular clusters did not form with the others. Designated NGC 2005, this system may be all that remains recognizable from a small dwarf galaxy the Large Magellanic Cloud merged with in the past. All other stars and gas from the former system have thoroughly mixed into the Large Magellanic Cloud, becoming indistinguishable from all the other stars that formed in other parts of our universe. After the break, we'll turn inward to our own solar system and talk about some recent planetary news. Stay tuned. In 2013, plumes of liquid were imaged erupting from the surface of Jupiter's moon Europa. These plumes came from geysers that sent freezing liquids up to 60 miles up. In a new study appearing in Geophysical Research Letters, author Lorenz Roth goes through the Hubble Space Telescope's archives looking for data that would allow them to measure the distribution of oxygen surrounding Europa. When looking at the trailing side of Europa, the team found both oxygen in the form of H2O molecules, that's water, and also molecular oxygen or O2. On the opposite leading side, only molecular oxygen is present. This is interpreted to mean that geysers are only on the trailing side of Europa. Like Earth's moon, Europa is tidally locked, so the same face is always facing Jupiter, and the same sides are always facing into its motion and away from its motion. Why this matters in the geysers? Well, the paper hints at tidal interactions and more observations are needed.
From Jupiter's moon Europa to Saturn's moon Titan, there are curious and interesting bodies in our solar system that, while they don't look like Earth, may share unexpected similarities. And one of those similarities is a kind of faulting we definitely see here on Earth, the strike slip fault. Just like the San Andreas fault here in California, strike slip faults occur when two plates push past each other, rubbing edges as they do. The edges stick, the strike part of the description, and occasionally unstick, the slip part of the description, causing medium to large quakes as they shift. We found these same types of faults on icy moons like Europa and Saturn's moon Enceladus, and now we've possibly found them on Titan. However, the mechanism differs between those moons. For Europa and Enceladus, the faulting is driven by the tidal stress on the moon by its gas giant and other moons. For Titan, which is as big as Mercury, the faulting may be the result of something more: pore fluid pressures that arise from all the liquid hydrocarbons on and beneath the surface. In particular, these shear faults seem to arise near the equator. Lead author of this new paper, published in Icarus, Lillian Burkhardt, notes, our results suggest that under these conditions, shear failure is not only possible, but may be an active deformation mechanism on the surface and in the subsurface of Titan, and could potentially serve as a pathway for subsurface liquids to rise to the surface. This can potentially facilitate material transport that could affect habitability. And now we wait for all those icy moon missions to launch, get to Jupiter and Saturn, and send back data. It's pretty amazing to me how much we still have to learn about our solar system. Joining me now is Dr. Julie Rathbun, a senior scientist at the Planetary Science Institute. Dr. Rathbun's research focuses on icy satellites in our solar system, but her particular love is Jupiter's volcanic moon Io. Io is the most volcanically active body in our solar system due to the constant push and pull of tidal stress from Jupiter and the other Galilean moons. Dr. Rathbun developed a model to explain how Loki, currently the most powerful volcano on the moon, operates. She has worked on numerous missions, including Cassini, New Horizons, and now the upcoming Europa Clipper, and we are very excited to have her with us today. Thank you and welcome, Dr. Rathbun.
Oh, thank you for having me.
So, I'm really excited to have you here because my favorite moon is Io. I'm sure I have mentioned this 1,000 times, and I know you have as well. So, how did you come to sort of have the same relationship with Io that I do?
It was actually kind of accidental. I sort of wandered into IO science. And it has to do with having a personal life. I was in a situation where my then boyfriend, now husband, moved from where we had been met and dating. It moved to a new location, and I wanted to work on a science project. I wanted to live near him, with him in the same city, and I was looking for a science project in that town and stumbled across Io and then fell in love with it.
That's fantastic. So, you started off, was Cassini the first mission that you worked on?
So I was never the first mission whose data I worked on was Galileo.
Oh, okay.
I was not officially a team member for either Galileo or Cassini, but I have used data obtained by both of them.
And did you use Galileo's data on Io?
Oh yes, that was actually the first data I looked at for Io was actually ground-based telescopic data, but then Galileo was a close second.
So, and I have a weird question, I think. Maybe not so weird. Are you responsible for naming Loki, or was that already named?
It was already named. I am not taking the blame for this one.
I think it's a great name, and I love that you've used it in your Twitter handle. So after working on the Galileo and Cassini data, you worked on New Horizons as well. What did you do with New Horizons?
So basically, my philosophy is anything that is looking at Io, I want those data. That's basically my philosophy. So the New Horizons spacecraft, as it headed out to Pluto, flew by Jupiter to get a gravity assist, as so many spacecraft do. Mm-hmm. And if you're in the Jupiter system, you might as well look at things in the Jupiter system. And the way the instruments were at the time, the way they were designed for low light conditions, they were actually quite difficult to use to look at anything in the Jupiter system in reflected sunlight. So what's interesting in the dark? Volcanoes. So they aimed a lot of the instruments, the spacecraft instruments at Io to obtain data. And I said, great, I can see what the volcanoes are up to. Give me those data, I'll look at them.
And what have you found out about Io? I know you've kind of figured out about Loki. What else have you discovered? What else have you learned? What have all these missions taught you so far?
So what I'm really trying to figure out is how do the volcanoes on this moon work? We do know that they are rocky volcanoes, just like volcanoes on Earth. Very low viscosity, so kind of more like a Hawaiian volcano than, say, something like Mount St. Helens.
Okay.
One of the things that I've been most interested in is how does the volcanic output change in time and space? In other words, there's something like 100 active volcanoes on Io at any given time. What controls which ones are active and when? Do ones at high latitude go off more often, less often? And does that change with time? And it's difficult to get enough data to understand this. I mean, ideally, we'd have some kind of, in my mind, we'd have some kind of dedicated instrument looking at Io all the time, so I could figure out which volcano is going off when, watches the volcano starts erupting, stops erupting, but we don't. So most of my time is spent figuring out how to use the data we have in ways that wasn't really intended to be used in order to answer these questions.
So Juno is supposed to do some flybys of Io. I know they've kind of patterned that in. Has any of that happened yet? Has any of that data come down yet? I'm not sure where we are in that.
That is a great question because we actually have a lot of Io data from the Juno mission already. Everybody's talking about the close flybys, but if all you want to know is which volcanoes are active and how active are they, you don't need to get a close flyby. So I've been using data that was obtained at a distance to answer those questions.
All right, I want to talk to you about this some more, but we're going to take a quick commercial break and we'll be right back with more with Dr. Julie Rathbun. All right, welcome back, Julie. Thank you for being here with us. So we were just talking about data you're getting from Juno. Have you had a chance to analyze any of the stuff that has come back so far?
We've looked at it a little bit, but first I want to mention why the Juno spacecraft is different and why it's so exciting for IO science. I mentioned earlier that I would like to know if volcanoes at high latitudes are different than those at low latitudes. So is there something happening that makes volcanoes near the equator different from those on at the poles? And there's some hints at this from the data we already have. However, all the data we already have is basically looking mostly at the equator. If you're looking from Earth, you're looking at the equator. If your spacecraft is in a normal orbit, you're looking from the equator. So all the data we have looks from the equator. So it makes it really hard to answer this question. Juno's orbit is polar. It was trying to answer questions about Jupiter's hemisphere by looking at Jupiter's poles. Since it's in this polar orbit, it also gets a great look at Io's poles. And so when I found this out, I just went, oh, this is fantastic. This is just the data I need. This is just the data I've been waiting for. Are you guys going to look at Io? And the answer I got was no. We're not looking at Io. It's not going to happen. And then I was meeting, and one of the instruments called GIROM, the Jovian Infrared Auroral Mapper, which was built by a group in Rome, Italy. One of their scientists was giving a talk, and they had data from the Galilean satellites. And so I hunted him down. I was like, wait, you guys have Io? Hold on a sec. Do you have any idea why this is important? And, these are folks who do an absolutely great job building instruments, but this instrument, it's in the name. It's designed to look at the Jupiter aurorae. It's not designed to look at Io's volcanoes. And so we started talking and we're like, okay, this is really cool. And so we've been talking quite a bit. We've analyzed about 3 orbits worth of data, which is not enough to give us an answer. What it is enough to do, I said earlier, I like using data to do something it's not designed for. It's given us enough time to figure out how to get out of it what we want, even though it's designed to do that. So we think we've gotten that figured out. And so we're hoping we can start going through all the data and actually get these questions answered. But I'm really looking forward to it.
So one of the papers that came out was talking about how the eruptions from Io, the particles that are getting out of the atmosphere, are actually getting swept up into Jupiter's magnetic field and pulled into the aurora, and actually are part of the reason that Jupiter has the aurora that it does. Did you work on that?
I don't. I'm more interested in the volcanoes, but certainly it's something interesting that the volcanoes are doing. When I was studying volcanoes, I never realized that they were the source of so much interesting phenomena in the Jupiter system. It's not just the aurora, it's the Io torus, it's other magnetospheric phenomena. It's just really cool to find out that volcanoes I just see lighting up are actually making these big changes in the entire system.
So just to wrap things up, what are you working on next?
concentrating on that Juno data. We're also continuing our ground-based observations, which are the absolute best way to see what Loki's doing. Loki is bright enough you can see it from the ground-based telescopes, and we can get observations from a telescope much more often than you can get observations from a spacecraft. And last time I checked, Loki was still erupting, though I expect it to dim and stop an eruption probably within the next month or so.
All right. Well, I look forward to all of the data and results coming out, and definitely we'll have you back on the show to talk about those next time something else happens. Really excited. Thank you for being here, Dr. Rathbun. It was lovely to speak with you, and we will chat again sometime soon, I'm sure.
Oh, great. Love to talk about IO whenever I can.
This has been The Daily Space.